Let's take a look at this problem from section 4.7, another optimization problem. And just to remind you, there's steps that you can take to help you solve for this optimization problem. We have to understand the problem, draw a diagram, have notation, find a function to optimize. This is where the real gist of it happens. Use constraints to write your function in terms of only one variable, and then find the max or min depending on what you're trying to do. This problem wants us to find the dimensions of a rectangle with a perimeter of 88 meters and whose area is as large as possible. So in terms of what we're trying to do here, this is understanding the problem is we want to find the dimensions. We want to find x and y so that this is as large as possible. So that's basically the first two steps. We're understanding the problem and we are trying to solve for it. And so let's take a look at how to solve for this. We have the area that we're looking for. It's x times y, and that's what we're trying to maximize. Now unfortunately what we have here is a function with two variables, x and a y, that are changing. And so we want to find a relationship between x and y, so that's called a constraint. We have another piece of information that says the perimeter is equal to 88. So x plus y plus x plus y is equal to 88. So that's the same thing as saying 2x plus 2y is equal to 88, which is what they have over here. And then if we solve for x or we solve for y, we're going to get 44 minus x. So if we solve for y, we bring the 2x on the other side as negative, and then we divide out by 2. So we get 44 minus x. Now that we have that, we're going to replace this y with x. So our new function is actually going to be a is equal to x times 44 minus x. And then as you can see, now this is a function of only one variable, x. That's going to be good for us. They also want us to find the domain, which is a good idea. And the domain here, if you imagine the perimeter x plus y plus x plus y, the whole thing is 88. This thing can get stretched down. You have 88 for x, and then the other x on top is going to go away. So our domain is really just going to go from 0 to 44. So a domain of 0 to 44. It's good to note. So we have x can go as low as 0. It actually, when it's equal to 0, then the area is going to be 0, which isn't going to make much sense, but we can include 0 or not include 0, so it doesn't really matter. So 0 less than x less than 44 is our domain. So now that we have that, we're going to take the derivative of your a function, and it's probably best if we multiply it all out. So that's an easy multiplication, right? So this is going to be 44x minus x squared. And then we take the derivative of that. So this would be a prime is going to be 44, and then we have a 2x. And if we set this equal to 0, this is going to be pretty easy to solve for because it's a linear function. We bring the 44 over to the other side. We're going to get negative 44 divide out by negative 2. It's going to be positive 22. So x is going to equal to 22. 22 is in fact between 0 and 44, which is good, so that we can find the absolute max and min. So they chose to use a second derivative test. This is A is actually a quadratic with a negative, so it's going to be concave down the whole way. You can also double check that by finding A double prime, and that's just going to be -2. It's constant, which means it has the same concavity all the way throughout, and that's just going to be a concavity of -2. So we have a -2 concave down. So the dimension of the rectangle is that x is going to be equal to 22, absolute maximum there. And then y, what was y equal to? Y is equal to 44 minus 22, or 44 minus x. That's also 22. So the dimensions of this is that x is 22 and y is 22. So dimensions of the rectangle, both values are the same, so you can just enter both numbers there. So it turns out that to maximize this, the square rectangle where both sides are the same is going to be the maximum value. I have a small graphic of the function and the box. We actually need to zoom out a little bit. So that we can take a look at the box. So the constraint tells us that the box is going to have to change dimensions according to what we have here. I also have the graph of the area function included. I think that's the area function, is whatever value of a and then the y value of 44a minus a squared. So to actually see that, I need to zoom out just a little bit more so we can find the point on the graph. If you look at the point on the graph, let's make this dark. We can see that the graph over here describes the area. Now we kind of don't see it in the picture anymore, but a 22 by 22 is going to give us the maximum value, and then the value at the extremes would be when x is equal to 0. That would be a super thin degenerate triangle, rectangle, and then at 44. Let's zoom out just a little bit more so we can actually see the maximum happen here. See, the maximum is happening over here at 22. Okay, and we see that little square. Let's do one more thing, take out the axis so that we can see the shape of the square or the rectangle going down to 0. Okay, so this is just a quick graphic of what's happening. The actual square that we're looking at is happening in blue, and then the graph of the function that we're trying to maximize, the area function, is this magenta colored parabola. All right, so I hope that helps.